What we have learned is that the moon has picked up a new tag along in space. This asteroid is called 2025 PN7. It's officially been called a quasi-moon.
Imagine looking up at the night sky and spotting something unusual. There, circling our moon, is another smaller object following its own orbital path. A moon with its own moon. It sounds like something out of science fiction, but before we explore whether such a thing could actually exist, we need to understand where our moon came from in the first place. The story of the moon's birth is one of the most dramatic events in our planet's history, and it takes us back an incredible 4.5 billion years.
Right. It's not the first time, and really there's two kinds of moons like this. There are these things that we call mini moons, which are actually sort of orbiting the Earth just like the moon and are captured by the Earth, and usually temporarily. They're all fairly small.
At that time, Earth was nothing like the blue marble we know today. The entire solar system was still in its chaotic infancy, with planets forming from clouds of gas and dust, and countless objects careening through space on unpredictable paths. It was during this violent period that something extraordinary happened, something that would forever change the fate of our planet. Scientists have developed what they call the Giant Impact Hypothesis, sometimes known as the Big Splash or the Theia Impact. According to this theory, there was once another planetary body in our cosmic neighborhood, roughly the size of Mars. Researchers have named this ancient world Theia, after the Greek goddess who was the mother of the moon goddess Selene. The name is fitting given what scientists believe happened next. Theia and the early Earth were both carving out their territories in the young solar system, orbiting the sun in paths that, unfortunately for both worlds, were destined to intersect. The laws of orbital mechanics made a collision inevitable. When these two massive objects finally met, the impact released energy on a scale that's almost impossible to comprehend. We're talking about two planet-sized bodies, each with tremendous mass, colliding at speeds of several kilometers per second. The collision itself would have been cataclysmic. According to research published by planetary scientists over the past few decades, the impact didn't completely destroy either world in the facet, traditional sense. Instead, it was more like a massive, glancing blow. Theia struck Earth at an angle, and the sheer force of the collision vaporized huge portions of both planets. Rock that had been solid moments before was instantly transformed into gas and molten droplets. The impact site would have glowed brighter than the sun, radiating heat across the surrounding space. What happened next is the key to understanding how the moon came to be. The collision ejected an enormous amount of material into space, perhaps as much as several percent of Earth's total mass. This debris didn't just fly off into the void, never to return. Instead, it remained in orbit around what was left of Earth, held in place by our planet's gravitational pull. Picture a massive ring of superheated rock, metal, dust, and gas, all circling the young Earth like a cosmic debris disk. According to computer simulations run by researchers studying planetary formation, this ring of material was incredibly hot, potentially reaching temperatures of several thousand degrees. The debris particles were constantly colliding with each other, sometimes breaking apart, sometimes sticking together. This process of accretion, as scientists call it, is fundamental to how celestial bodies form throughout the universe. Over the course of the next few million years, gravity did its work. Larger chunks of debris attracted smaller ones, growing bigger with each collision. The biggest accumulations attracted even more material, growing faster than their smaller neighbors. Eventually, one mass dominated the debris ring, sweeping up most of the available material in its orbital path. This growing sphere of molten rock was the proto-moon, and it was being born through the same basic process that had formed the planets themselves. The early moon would have been a hellish place. Its surface was likely covered in an ocean of molten lava, radiating heat into space. But gradually, over hundreds of thousands of years, it began to cool. The outer layers solidified first, forming a crust over the still molten interior. During this time, the moon was also much closer to Earth than it is today, perhaps only 20,000 to 30,000 kilometers away, compared to the current distance of about 384,000 kilometers. Evidence supporting this giant impact hypothesis comes from multiple sources. When NASA's Apollo missions brought back samples of lunar rock between 1969 and 1972, scientists were able to analyze the moon's composition in detail for the first time. They discovered some fascinating things. The moon's chemical makeup is remarkably similar to Earth's mantle, the layer of rock beneath our planet's crust. This similarity makes sense if the moon formed from material blasted out of Earth during a collision. Additionally, the moon has a much smaller iron core relative to its size compared to Earth. If the moon had formed independently as a separate planet, we'd expect it to have a larger core. But if it formed from the outer layers of Earth and Theia, which had already differentiated their heavy elements into their cores, then a small lunar core is exactly what we'd predict. There's also the matter of the moon's lack of volatile elements, substances that evaporate easily. The moon is quite dry compared to Earth and has very little in the way of elements like hydrogen and nitrogen. This fits with a formation scenario involving an incredibly hot debris disk where lighter volatile materials would have been vaporized and escaped into space, leaving behind the heavier rocky material that eventually became the moon. Recent isotope analysis has provided even more compelling evidence. Studies published in scientific journals over the past decade have shown that Earth and Moon rocks have nearly identical isotopic signatures for several elements, including oxygen, titanium, and tungsten. This is significant because different parts of the solar system tend to have distinct isotopic fingerprints. If the Moon had formed somewhere else and been captured by Earth's gravity, or if it had formed alongside Earth from the same disk of material without a giant impact, we'd expect to see more differences in these isotopic ratios. The giant impact hypothesis isn't just important for understanding our own moon. It's taught scientists a lot about how planetary systems evolve in general. We now know that massive collisions were probably quite common in the early days of solar systems throughout the galaxy. In fact, such violent events may be a normal part of how rocky planets grow to their final sizes. So this is the story of how Earth got its companion through one of the most violent events imaginable. But knowing how our moon formed raises an interesting question. If moons can form from massive impacts and if they can be captured by gravitational forces, could a moon itself capture its own, smaller moon? Could the moon have a moon of its own, and if such a thing appeared, would we be looking at another giant impact waiting to happen? The formation of our moon through a catastrophic impact is certainly dramatic, but it's worth pointing out that this isn't the only way moons come into existence. And understanding these alternative pathways is crucial if we want to explore whether a moon could have its own moon. So before we imagine what it would be like if such an object appeared in orbit around our lunar companion, let's look at how some of the other moons in our solar system came to be. Not every moon required millions of years and a cloud of debris to form. Some moons in our solar system have a much simpler origin story. They're captured objects, celestial wanderers that happened to pass too close to a planet and found themselves permanently trapped by its gravitational pull. This process of gravitational capture is actually quite common throughout the cosmos, and it can happen relatively quickly compared to the eons-long process that created our moon. One of the best examples of a captured moon is Triton, the largest of Neptune's 13 known moons. Triton is fascinating for several reasons, but the most telling clue about its origin is the direction it orbits. Unlike most large moons in the solar system, which orbit in the same direction their host planet rotates, Triton moves in what astronomers call a retrograde orbit. It circles Neptune in the opposite direction to the planet's spin. This is a huge red flag that something unusual happened in Triton's past. Planetary scientists studying Triton's composition and orbit have concluded that this moon almost certainly didn't form alongside Neptune. Instead, researchers believe Triton was once an independent object, possibly similar to Pluto, wandering through the outer reaches of the solar system in a region known as the Kuiper Belt. This is a vast expanse beyond Neptune's orbit that contains countless icy bodies, remnants from the formation of our solar system. At some point in the distant past, perhaps billions of years ago, Triton's path brought it close to Neptune. Exactly what happened next is still debated by scientists, but the most widely accepted theory involves a close gravitational encounter that robbed Triton of enough orbital energy to prevent it from escaping. Some researchers suggest that Triton might have been part of a binary system, two objects orbiting each other, and that Neptune's gravity separated them, capturing one while flinging the other away into space. Once trapped in Neptune's gravitational field, Triton's orbit would have been highly elliptical, bringing it very close to Neptune at some points and very far away at others. Over millions of years, the gravitational interactions between Neptune and Triton, along with tidal forces, gradually circularized the orbit into the nearly circular path we see today. This process would have generated enormous amounts of heat within Triton, possibly explaining why it still shows signs of geological activity despite being one of the coldest objects in the solar system. Now, if a massive planet like Neptune can capture a moon as large as Triton, could our own moon capture something smaller? Could we wake up one morning to find that the moon has acquired its own satellite, a submoon, or, as some scientists playfully call it, a moon-moon or even a moon-moon? It's a legitimate scientific question, and researchers have actually studied the possibility. Let's imagine the scenario. A small asteroid, perhaps a kilometer or so across, is traveling through the inner solar system on its regular orbit around the Sun. Its path brings it close to Earth, but not so close that it enters our atmosphere or collides with our planet. Instead, it passes by at just the right distance, and at just the right speed to bring it even closer to the Moon. If the geometry is absolutely perfect, the asteroid might find itself captured not by Earth, but by the Moon's own gravitational field. This would be an incredibly delicate balancing act. The object would need to have exactly the right velocity and trajectory. Too fast, and it would zip past the Moon and continue on its way. Too slow, and it might crash into the lunar surface. The capture would require the asteroid to shed just enough orbital energy, perhaps through a complex gravitational interaction, to become bound to the Moon without being destroyed in the process. Research published by orbital dynamics specialists suggests that for such a capture to result in a stable orbit, the object would need to be quite small, probably no larger than a kilometer in diameter. Anything bigger would create too much gravitational disturbance, potentially affecting the Moon's own orbit around Earth. The asteroid would need to be a Goldilocks object, not too big and not too small, with just the right properties to settle into a sustainable orbit. But even if all these conditions were met and the Moon successfully captured its own satellite, the story wouldn't end there. In fact, according to calculations by astronomers studying multi-body orbital mechanics, it would really just be the beginning of a relatively short and unstable chapter. The fundamental problem is that this moon-moon would exist in what physicists call a three-body system, and three-body systems are notoriously chaotic and unpredictable. The moon-moon would be constantly subjected to gravitational tugs from three different sources. First, there's the Moon itself, which captured it in the first place. Then there's Earth, whose much stronger gravitational field dominates this entire region of space. And finally, there's the Sun, whose gravity affects everything in the solar system. These competing gravitational influences would create what are known as tidal forces, essentially pulling the moon-moon in different directions at different times. Over the course of weeks, months, or perhaps a few years at most, these complex interactions would destabilize the moon-moon's orbit. The object might gradually spiral outward, eventually escaping the Moon's gravitational influence entirely and returning to an independent orbit around the Sun. Alternatively, it might spiral inward, getting closer and closer to the lunar surface until it finally impacts, creating a new crater on the Moon's already heavily cratered face. There's even a possibility that it could be ejected from the Earth-Moon system entirely, flung out into a completely different part of the solar system. Studies by researchers using computer simulations to model these scenarios suggest that the typical lifespan of such a moon-moon would be measured in years or perhaps decades, not the millions or billions of years that characterize stable moons elsewhere in the solar system. It would be a temporary visitor, a cosmic curiosity, rather than a permanent fixture. During its brief existence, the moon-moon would have virtually no physical effect on Earth itself, an object only a kilometer across, orbiting the Moon. Rather than our planet, wouldn't generate any noticeable tidal forces down here. We wouldn't see changes in our ocean tides, and the length of our days wouldn't be affected. For all practical purposes, daily life would continue exactly as before. But that doesn't mean the moon-moon would go unnoticed. Quite the opposite. Throughout human history, the Moon has held a special place in our cultures, religions, and mythologies. Ancient civilizations built monuments aligned with lunar phases. Countless stories, poems, and songs have been inspired by Earth's silver companion in the night sky. The sudden appearance of a smaller object orbiting the Moon would trigger an unprecedented wave of public interest. Amateur astronomers with backyard telescopes would be among the first to spot it, and social media would explode with images and speculation. Scientists would rush to point every available telescope at this new phenomenon, eager to study its composition, orbit, and behavior. There would undoubtedly be wild conspiracy theories about where it came from and what it might mean. Some might see it as an omen, others as proof of various fringe ideas about the solar system. For the scientific community, however, the moon would represent an extraordinary opportunity. Never before would we have had the chance to observe a natural satellite system so close to home, one that we could study in exquisite detail. Astronomers could track how the orbit evolves over time, testing their understanding of gravitational dynamics against real-world observations. The data collected could help us better predict similar scenarios occurring around other planets in distant solar systems, improving our general understanding of how multi-body systems behave. But eventually, perhaps after a few years of intensive study and public fascination, the show would come to an end. One of three things would happen. We might watch as the moon gradually drifts away, its orbit expanding until it breaks free from the moon's hold and disappears back into the darkness of space. Or we might witness it spiral inward, ending its journey with a dramatic impact on the lunar surface, an event that would likely be captured by numerous telescopes and cameras. There is, however, a third possibility, one that's less likely but far more concerning. In the chaotic gravitational environment created by the Earth-Moon-Moon-Moon system, there's a small chance that the asteroid could be perturbed onto a collision course, not with the Moon, but with Earth itself. If a small moon colliding with Earth sounds concerning, let's consider something even more extreme. What if the roles were completely reversed? What if Earth suddenly shrank down to the size of the Moon, and the Moon expanded to become as large as Earth? This thought experiment might sound absurd, but it's actually a useful way to understand the fundamental forces that govern planetary bodies and what makes Earth such a special place for life. Before we dive into the chaos that would unfold, let's establish some ground rules for this scenario. When we say Earth shrinks to the size of the Moon, we're talking about everything on Earth becoming proportionally smaller. All the continents, mountains, oceans, the iron core, even the crust would be compressed down to roughly a quarter of their current size. To keep things clear, let's call this miniaturized version Little Earth. Meanwhile, the Moon would balloon outward to Earth's current size, and we'll refer to this expanded version as Big Moon. Here's the crucial point though. While Little Earth itself would shrink, everything living on it, including humans, animals, and plants, would remain their current size. This creates an immediate problem. Imagine trying to fit the entire human population, along with all the infrastructure of modern civilization, onto a sphere that's now only about a quarter of its former diameter. The overcrowding would be catastrophic right from the start. But overcrowding would quickly become the least of our concerns, because the real problems start with gravity. For any celestial body, gravitational force depends on two main factors: mass and radius. Little Earth's radius would shrink to about 1/4 of its current value, which sounds significant. But the mass change would be even more dramatic. Little Earth would retain only about 2% of its original mass. This is because when you shrink a sphere, you're reducing its volume, and volume decreases with the cube of the radius. A planet 1/4 the size has roughly 1/64 the volume, and therefore much less mass. This massive reduction in both size and mass would fundamentally alter the gravitational environment at the surface. Scientists studying planetary gravity have established that surface gravity depends on mass divided by radius squared. When you plug in the numbers for Little Earth, you end up with a surface gravity of only about 27% of what we currently experience. In practical terms, if you weigh 70 kilograms on regular Earth, you'd weigh just 19 kilograms on Little Earth. At first glance, this might seem like good news. Who wouldn't want to weigh less? Moving around would certainly feel different. You'd be able to jump higher and carry objects that would normally be too heavy with ease. Walking would feel bouncy, almost like the footage we've seen of astronauts exploring the lunar surface, except you wouldn't need a bulky spacesuit. Activities requiring strength would become trivially easy for most people. The reduced gravity would also have interesting implications for transportation and geography. With the planet shrunk to a quarter of its size, distances between cities would be dramatically reduced. The journey from New York to Paris, currently about 6,000 kilometers requiring a 7-hour flight, would shrink to roughly 1,500 kilometers, achievable in under 2 hours. With Lower gravity aircraft would require less fuel to achieve liftoff, and maintaining altitude would be easier. Rockets launching into space would have a much easier time escaping little Earth's weakened gravitational pull. But before we get too excited about the convenience of lighter weight and shorter travel times, we need to confront the harsh biological reality. Humans evolved over millions of years under Earth's current gravitational conditions. Our bodies are specifically adapted to function in an environment where gravity pulls us downward with a force of about 9.8 meters per second squared. Remove that constant force, and our biology starts to malfunction in concerning ways. We actually have extensive data on what happens to the human body in low-gravity environments, thanks to decades of research aboard space stations. Astronauts spending extended periods in microgravity experience rapid physiological changes. Studies conducted by space agencies have documented that astronauts can lose up to 13% of their muscle mass in just 6 months in space. While the gravity on little Earth wouldn't be zero, it would still be dramatically lower than what our bodies need to maintain healthy muscle tissue. The problems go well beyond muscle loss. Your skeleton would also suffer. Bones are living tissue that constantly remodel themselves in response to the stresses placed upon them. In lower gravity, your bones would experience less stress, triggering a process where bone density decreases. Your spine would be particularly affected. Without the constant compression from normal Earth gravity, the discs between your vertebrae would expand, causing your spine to lengthen. This might sound beneficial, but it actually leads to chronic back pain and can cause lasting damage to your spinal structure. Medical researchers studying astronaut health have identified another peculiar consequence of low gravity that they've termed puffy face bird leg syndrome. On Earth, gravity pulls bodily fluids downward toward your feet. Your cardiovascular system has adapted to pump blood upward against this force. In reduced gravity, fluids redistribute themselves more evenly throughout the body, or even pool in the upper body and head. The result is a swollen, puffy face and thinner legs, hence the somewhat comical but accurate name. This fluid redistribution also causes problems with vision, as increased pressure in the head can damage the optic nerve and eyeball structure. While little Earth's inhabitants would be struggling with these biological challenges, the Big Moon would be undergoing its own dramatic transformation. Expanding to match Earth's diameter, the Big Moon would end up weighing about 2/3 as much as the original Earth. This might seem like it would have less mass than Earth, but remember, we're comparing it to the original Earth, not Little Earth. Relative to Little Earth's meager 2% of original Earth mass, Big Moon would be a gravitational giant. The gravitational pull at the Big Moon's surface would increase substantially from the Moon's current weak gravity. Right now, standing on the lunar surface, you'd experience a gravitational acceleration of only 1.62 meters per second squared. But the Big Moon's gravity would jump to approximately 6 meters per second squared, roughly 60% of the original Earth's gravitational pull. This is a massive increase, and it would have serious implications for everything in the vicinity, particularly for Little Earth itself. The relationship between Earth and Moon has always been gravitationally complex. Currently, the Moon's gravity is strong enough to create tidal bulges in Earth's oceans. As different parts of Earth rotate through these bulges, we experience high and low tides. On our current Earth, typical tides rise and fall by about 1 meter, give or take, depending on location and lunar phase. This is a manageable amount of water, movement that coastal communities have adapted to over millennia. But with the Big Moon's dramatically increased gravitational pull acting on Little Earth, everything would change. The tidal forces would become enormously more powerful. What we currently experience as a gentle 1 meter tide would transform into massive walls of water, essentially tsunamis occurring twice daily. Coastal cities that currently thrive at sea level would be completely uninhabitable. Major population centers like New York, London, Venice, Tokyo, and countless others would be repeatedly inundated with devastating floods. The death toll would run into the hundreds of millions as coastal infrastructure was swept away. The destruction wouldn't stop at the coastlines. The Big Moon's gravity would be strong enough to deform Little Earth itself, not just its oceans. The solid rock of the planet's crust and mantle would experience tidal forces similar to what the oceans undergo, just to a lesser degree. This constant gravitational kneading would generate enormous internal stresses within Little Earth. The result would be catastrophic geological activity. Earthquakes would become far more frequent and severe as the planet's crust buckled and fractured under the tidal stresses. Existing fault lines would become hyperactive. But even more concerning would be the effect on little Earth's interior. The planet's mantle and core would be subjected to intense gravitational forces that would heat them through friction. Researchers studying planetary geology have observed similar processes elsewhere in the solar system. Jupiter's moon Io provides a clear example. Io is caught in a gravitational tug-of-war between Jupiter and other nearby moons, and this constant flexing generates so much internal heat that Io is the most volcanically active body in the entire solar system. Little Earth would face a similar fate. Volcanoes that had been dormant for thousands or millions of years would roar back to pursuits, life. New volcanic vents would open up across the planet's surface. The combination of constant earthquakes and volcanic eruptions would make Little Earth's surface incredibly hostile to life. Remember earlier when I mentioned you wouldn't need a spacesuit on Little Earth because of its atmosphere? Well, it's time to take that back. You would absolutely need one, and the reason has to do with one of the most fundamental requirements for life as we know it. Little Earth is going to lose its atmosphere, and it's going to happen remarkably quickly. Earth's atmosphere is a precious thing. It's a relatively thin shell of gases, mostly nitrogen and oxygen, held in place by our planet's gravitational pull. Every molecule of air is constantly trying to escape into space, pulled upward by its own kinetic energy and thermal motion. What keeps our atmosphere from drifting away is gravity. Earth's gravitational field is strong enough to hold onto these gas molecules, preventing them from reaching escape velocity. But Little Earth's gravity would be only 27% of what we currently have. That's a catastrophic reduction in the planet's ability to retain its atmospheric gases. Scientists studying planetary atmospheres have established that there's a relationship between a planet's mass, its gravity, and its ability to hold onto an atmosphere. When gravity weakens significantly, lighter molecules start to drift away into space. The process begins gradually but accelerates over time. Within years, perhaps even months, the upper layers of Little Earth's atmosphere would begin to thin noticeably. The lightest gases, including hydrogen and helium, would be the first to go. But eventually, even heavier molecules like nitrogen and oxygen would start to escape. The atmospheric pressure at the surface would drop steadily. Breathing would become difficult, then impossible, without supplemental oxygen. Interestingly, some of Little Earth's escaping atmosphere might not be lost to space entirely. The Big Moon, with its newfound substantial gravity, could potentially capture some of these gases. Over time, the Big Moon might accumulate enough atmospheric material to develop a thin atmosphere of its own. It's a strange irony that Little Earth's loss could become Big Moon's gain, potentially making the expanded lunar surface slightly more hospitable than it is today. But even if Little Earth managed to cling to some remnant of its atmosphere through some unknown mechanism, there's a second, slower process that would ultimately strip it away. This process is tied to something happening deep within the planet, in its molten core. Little Earth's smaller size would have profound implications for its internal heat budget. Planets generate and retain heat through several mechanisms. There's primordial heat left over from the planet's formation, heat generated by radioactive decay of elements in the interior, and heat produced by tidal forces. But planets also lose heat, radiating it away into space. The rate at which a planet loses heat depends on its surface area, while the amount of heat it contains depends on its volume. When you shrink a planet, its surface area to volume ratio changes dramatically. Little Earth would have much less volume compared to its surface area than regular Earth does. This means it would cool down much faster. Planetary scientists studying thermal evolution have calculated that smaller bodies lose their internal heat more rapidly than larger ones. We can observe this principle throughout the solar system. The Moon, Mars, and Mercury all cooled relatively quickly after their formation and now have solid, inactive interiors. Earth, being larger, has retained its internal heat for over 4 billion years and remains geologically active. The cooling of Little Earth's core would have consequences that extend far beyond geology. Earth's magnetic field, the invisible shield that protects us from harmful solar radiation, is generated by the motion of molten iron in the outer core. This process, called the geodynamo, requires a liquid outer core with convection currents driven by heat. As Little Earth's interior cools, these convection currents would slow down and eventually stop. Research on planetary magnetic fields suggests that the Moon once had its own magnetic field billions of years ago when its interior was still hot and molten. Analysis of lunar rocks brought back by the Apollo missions revealed magnetic minerals that had been magnetized by an ancient lunar magnetic field. But that field disappeared as the moon cooled and its core solidified. Scientists estimate this process took roughly 200 million years. Little Earth would follow a similar trajectory. Over the course of hundreds of millions of years, its magnetic field would weaken and ultimately vanish. This might seem like a problem for the distant future, but the consequences would begin immediately. Earth's magnetosphere doesn't just generate pretty auroras when it interacts with charged particles from the sun. It serves as a crucial protective barrier against the solar wind, a constant stream of charged particles flowing outward from the sun at speeds of hundreds of kilometers per second. Without a magnetic field to deflect these particles, the solar wind would strike Little Earth's atmosphere directly. Over geological timescales, this bombardment would strip away atmospheric gases, carrying them off into space. Mars provides a sobering example of this process. The red planet lost its magnetic field billions of years ago, and solar wind has been steadily eroding its atmosphere ever since. What was once a thicker atmosphere capable of supporting liquid water on the surface has been reduced to less than 1% of Earth's current atmospheric pressure. The combination of low gravity and the eventual loss of the magnetic field would doom Little Earth's atmosphere. But the problems for any surviving inhabitants would extend beyond the inability to breathe. Without an atmosphere, Little Earth would lose the moderating influence that air provides to surface temperatures. On Earth, our atmosphere acts like a blanket, trapping heat from the sun during the day and preventing it from radiating away too quickly at night. This keeps temperatures relatively stable and livable. On Little Earth, without an atmosphere to distribute and retain heat, temperatures would swing wildly between day and night. During the day, when the sun was overhead, the surface would heat up dramatically, potentially reaching temperatures well above the boiling point of water. At night, without the sun's warmth and without an atmosphere to trap residual heat, temperatures would plummet to well below freezing. These extreme temperature swings would make the surface incredibly hostile to any form of life. Water, that essential ingredient for life as we know it, would not fare well in this new environment. As the atmosphere thinned and surface temperatures became more extreme, liquid water would become increasingly unstable. During the scorching days, water would evaporate rapidly. During the freezing nights, it would turn to ice. Without atmospheric pressure to keep water in its liquid state, Earth's oceans, the vast bodies of water that cover 70% of our current planet's surface, would gradually boil away into space or freeze at the poles. Little Earth might retain some water ice at its polar regions, similar to what we observe on Mars today. But the liquid oceans that teem with life, regulate climate, and make Earth unique among known planets would be gone. With them would go the vast majority of Earth's biodiversity and any hope of maintaining the ecosystems that support human life. Any humans who somehow survived this far would face additional threats beyond the obvious ones of being unable to breathe and dealing with extreme temperatures. Without the protective shield of the atmosphere and magnetosphere, the surface would be bombarded by high-energy radiation from the sun and from cosmic rays originating in deep space. This radiation includes ultraviolet light, X-rays, and charged particles, all of which are harmful to living tissue. Medical research on radiation exposure has shown that even relatively low doses of ionizing radiation increase cancer risk. Higher doses can cause acute radiation sickness, damage to the nervous system, and a range of other health problems, including cataracts and immune system dysfunction. On Little Earth's exposed surface, radiation levels would be many times higher than what we experience on Earth today, where our atmosphere and magnetic field provide effective shielding. Anyone spending extended time on the surface without heavy radiation protection would face almost certain development of cancers and other radiation-induced illnesses. But while all these catastrophes would be unfolding on Little Earth, an even more fundamental change would be taking place over millions of years, one that would alter the very nature of our planet's relationship with the Big Moon. This change involves a phenomenon called tidal locking, and it's something we can already observe in the current Earth-Moon system. Right now, the Moon is tidally locked to Earth. This means the Moon takes exactly the same amount of time to rotate once on its axis as it takes to complete one orbit around Earth. The result is that the same side of the Moon always faces our planet. We never see the far side of the Moon from Earth, not because it's perpetually dark, that's a common misconception, but because it's always pointed away from us. Tidal locking occurs because of gravitational interactions between two bodies. The larger body, in this case Big Moon, exerts tidal forces on the smaller body, Little Earth. These forces create friction within Little Earth, gradually slowing its rotation. Over millions of years, this rotational slowing would continue until Little Earth's rotation period matched its orbital period around the Big Moon. But here's where things get really interesting. Once tidal locking is complete, Little Earth would always show the same face to Big Moon. One hemisphere of Little Earth would have the Big Moon perpetually visible in the sky, while the other hemisphere would never see it at all. The planet would be divided into two distinct regions, the Big Moon-facing side and the far side. This tidal locking would also fundamentally change what it means for Little Earth to be a planet. In our current solar system, we define planets as objects that orbit the Sun and have cleared their orbital neighborhoods. Moons, by contrast, orbit planets. After tidal locking and the gravitational settling of the system, Little Earth would primarily orbit the Big Moon, not the Sun. Little Earth would, by definition, have become a moon. The Big Moon would be the planet, and Little Earth would be its natural satellite. The length of a day on. Little Earth would change dramatically as well. Currently, Earth completes one rotation in 24 hours, giving us our familiar day-night cycle. But a tidally locked Little Earth would take much longer to complete one rotation. If the orbital period ended up being similar to our current lunar month, a single day on Little Earth could last nearly 30 Earth days. You'd experience about 15 days of continuous sunlight, followed by 15 days of darkness. This extended day-night cycle would create its own set of problems. The day side would have plenty of time to heat up under continuous sunlight, reaching scorching temperatures. The night side would have equally long to cool down, potentially becoming unimaginably cold. The terminator, the line separating day from night, might be the only region with somewhat moderate temperatures, though even that would be a harsh environment without an atmosphere. At this point, after considering all the disasters that would befall Little Earth, tsunamis, earthquakes, volcanoes, atmospheric loss, extreme temperatures, deadly radiation, and the fundamental transformation into a moon, you might be wondering if there's any hope for humanity at all. The answer might lie in looking upward at the Big Moon. Big Moon would actually have some advantages over Little Earth. For one thing, it would have significantly more gravity, about 60% of the original Earth's gravitational pull. While this is less than what we're adapted to, it's far more than Little Earth's paltry 27%. This stronger gravity would be better for human health and would make the Big Moon more capable of retaining an atmosphere if one could be created. Additionally, the Big Moon would still be in the habitable zone around the Sun, that narrow range of distances where temperatures allow for liquid water to exist on a planet's surface. The Big Moon would receive the same amount of solar energy that Earth currently receives, which is exactly what we need for a comfortable climate. The main problems with the Big Moon would be its lack of atmosphere and liquid water, but these aren't necessarily insurmountable obstacles. Some scientists and engineers have proposed methods for terraforming planetary bodies, transforming them into habitable worlds. For the Big Moon, one approach would involve breaking open the crust to release gases trapped beneath the surface. The most extreme version of this idea involves using nuclear weapons to crack open the surface in strategic locations. The explosions would create massive fractures in the crust, allowing subsurface gases to escape and begin forming a primitive atmosphere. This might sound like science fiction, but researchers studying planetary engineering have seriously considered such approaches. With the Big Moon's increased gravity, it would have a better chance of holding onto these released gases than the original moon would. Water would be the next challenge. The current moon has substantial deposits of water ice at its poles, in permanently shadowed craters where temperatures never rise above freezing. Studies by lunar scientists estimate there could be billions of tons of this ice. With Big Moon's larger size, there would presumably be even more ice available. This ice could be extracted and melted, providing water for human use and potentially helping to establish a water cycle if an atmosphere could be maintained. With water and a basic atmosphere in place, the next step would be introducing plant life. Plants could help transform the Big Moon's atmosphere through photosynthesis, gradually increasing oxygen levels while removing carbon dioxide. This process would take centuries or millennia, but it would represent the beginning of making the Big Moon genuinely habitable. One advantage that Little Earth would provide in this scenario is that its lower gravity would make launching spacecraft much easier. Currently, escaping Earth's gravity well requires enormous amounts of fuel, and powerful rockets. But launching from Little Earth would require far less energy. This would make it more feasible to transport supplies and equipment to Big Moon, supporting the construction of settlements and terraforming infrastructure. Advanced spacecraft technology could establish regular transport between Little Earth and Big Moon, allowing humanity to slowly migrate to the more promising world while using Little Earth as a staging ground. It would be a monumental undertaking requiring resources, technology, and determination on an unprecedented scale. But throughout history, humans have shown a remarkable ability to adapt to challenging circumstances and overcome seemingly impossible obstacles. Of course, there's always another option. Instead of trying to terraform the Big Moon or struggling to survive on Little Earth, humanity could set its sights even further out and focus efforts on reaching Mars, but that's a question for another time, another scenario to explore in the endless realm of what if.